Imagine traveling at 320 km per hour. No traffic, no turbulence, no pilot, just pure speed on steel. This isn't science fiction, this is a bullet train. A train so fast that cities shrink, distances disappear, and time feels cheated. But here's the real mystery. How does a 400-ton machine move faster than a car on a highway and still remain safe? Today we decode the hidden science, engineering secrets, and mind-blowing technology behind the bullet train. Stay till the end, because what you'll hear might change how you see transportation forever. Bullet trains are officially called high-speed trains. The name bullet train comes from Japan's Shinkansen, launched in 1964. Why bullet? Long nose, extreme speed, straight, smooth motion. Unlike normal trains, no sharp turns, no road crossings, no mixed traffic. They run on dedicated tracks built only for speed. Key speeds: normal train 80 to 130 km per hour, express train 160 to 200 km per hour, bullet train 300 to 350 plus km per hour. But speed alone is not the real miracle. You cannot run a Formula 1 car on a village road. Same logic applies to bullet trains. Why normal tracks don't work. At high speed, tiny bumps become dangerous. Vibrations multiply, wheels can derail bullet train tracks, extra straight alignment, gentle curves, huge turning radius, no level crossings, elevated or fenced tracks. Even a 1 centimeter error can cause disaster. That's why bullet train tracks are engineered to millimeter precision. Unlike planes, bullet trains do not float, except maglev. They use steel wheels on steel rails. Sounds risky? Actually, steel on steel gives less friction, higher efficiency, better durability. Each wheel is precisely shaped, self-centering, designed to balance at extreme speed. At 300 km per hour, wheels rotate 2 to 500 plus times per minute. Even slight imbalance is vibration disaster. That's why maintenance is extreme. Speed is not the enemy, air is. At high speed, air becomes a solid wall. Why the long nose? Japanese engineers studied kingfisher birds. When a bullet train enters a tunnel, air pressure explodes, causes loud tunnel boom. The long nose reduces pressure waves, cuts air resistance, saves energy. Modern bullet trains are more aerodynamic than some airplanes. Bullet trains don't have one engine. Every coach has motors. This is called distributed traction. Why electricity? Cleaner, faster acceleration. Precise control power comes from overhead electric lines, pantograph collectors, electricity feeds, traction motors, braking systems, control computers. Acceleration feels smooth because power is spread evenly. Stopping a bullet train is harder than making it fast. Bullet trains use 3 braking systems. 1. Regenerative braking motors. Act like generators. Electricity sent back to grid 2. Disc brakes used at lower speeds. 3. Emergency brakes, powerful, rare last option. Even then, stopping distance is 3 to 4 km. That's why planning is everything. Shocking fact: Japanese bullet trains have 0 fatal accidents in 60 plus years. Why? Safety systems, earthquake detection, automatic speed control, no human signal dependence, real-time monitoring. If danger detected, power cuts, brakes activate. Train stops automatically, human error is almost eliminated. Now imagine no wheels. Maglev trains float using magnetic force. Zero friction speeds, 600 plus km per hour, Japan's maglev test, 603 km per hour record. But challenges: extremely expensive, special tracks, high energy cost. Still, this is the future of ultra-speed travel. Countries with bullet trains: Japan, China, France, Germany, India's Mumbai-Ahmedabad bullet train, Japanese Shinkansen tech. Speed 320 km per hour. Travel time 82 hours. This will redefine Indian transport. Bullet trains are not just machines, they are proof that engineering can bend time. From steel wheels to magnetic floating, from slow journeys to same-day cities,